Unit 7, pages 228 to 230. So a cross section is what we get when you cut into a bone and that flat piece of the cut is then six inches. So the cross section that piece will cut. Similarly for an isosceles an equilateral triangle, right? You cut something open and on the front side. These are the shapes. So if our cross sections are if this is considered the solid or the base of the solid, and then we cut and open and we get a square as our cross section, then the length of the square is going to be our upper function, which is f of x, minus our lower function, which is g. And that's going to be the same for all of these cross sections. F of x represents the upper function, and g of x represents the lower function. Okay, so to get the length of this cross section, it'll be f of x minus g. And since it's a square, both sides will be the same length. And now we're going to find the area of this. And we know that our area of a square is equal to whatever side squared. So that means that our area is going to be f of x minus f. Right, because that's the cross section. So if we want to add up all the areas of these squares, because we're looking at a solid as a whole that has square cross sections, if all the cross sectional areas are added up, total would be the volume of the solid that was fixed above. So when we're adding up all of these solids, find the volume, that's when we bring in our integral sign. So what our from A to B of our area minus b of x squared dx. Because we're going to add up all of the areas of the square. So for each square that's in this picture, the length of it is f x minus c of x at different values of x. Right, so similarly here we have an equilateral triangle. We know the area of a triangle is equal to half base times height. And then that equals an isosceles right triangle. So we know that the length of the base and the length of the height are going to be the same. So here's my base and here's my height. And those are going to be the same because it's isosceles. The sides are the same. And if you look at the length of the base is equal to our upper function, which is f of x, minus our lower function, which is g of x. So then the area of this triangle will be equal to 1/2. Our base is f minus g of x times our height, which is f of x minus g of x. So we get the area is equal to 1/2 f of x minus g of x squared. And once again, if we add up all of those cross sections, we'll get that the volume is equal to the definite interval from a to b of 1/2 f of x minus g of x squared. And we can bring that 1/2 out and we get volume is equal to 1/2 definite interval from a to b of f of x minus g of x squared. Yeah. Okay. So now we're going to look at cross sections that are equilateral triangles and cross sections that are semicircles. So equilateral triangles are the triangles where all the side lengths are the same. So if we look at this cross section, the base of this triangle is again going to be some upper function f of x minus some lower function g of x. So to find the height of this triangle, as we know the area of a triangle is 1/2 base times height. Our base is f of x minus g of x. So we need to now find the height of this triangle. And to do that, we need to identify the type of triangle that can be created by splitting an equilateral triangle in half. So by splitting an equilateral triangle in half, we get a 90 triangle. And those side lengths are proportional in a specific way. Right? So if the base is plus the hypotenuse is 2x, and the long side is square root of 3x. So in this case, our x is going to be equal to half of our base. So then the height is equal to square root of 3 times half of our base. So we have square root of 3 times 1/2 of f of x minus g of x. So our area function is 1/2 times our base, which is f of x minus g of x, times our height, which is square root of 3 f of x minus g of x, which we can simplify to being square root of 3 over 2, square root of 3 over 4, squared. So if we add up all of these areas, this would turn into is equal to definite interval from a to b of root 3 over f minus g of x squared dx, which we can simplify to bring up the root 3 over times the definite interval from a to b f of x minus squared dx. Okay, so now we have a semicircle. So we cut open this solid, we cut slivers of semicircles. The area of a semicircle is equal to 1/2 pi r squared. So then to find this area, we needed to know what r is. So if the whole face of my semicircle is some f of x, some upper function, minus some lower function g of x. That would be the entire diameter. So to find the radius, we're going to take half of the diameter. So that's 1/2 f of x minus g of x. So the area function will be equal to 1/2 pi times 1/2 f of x minus g of x squared. And when we simplify this, we get area is equal to 1/2 pi times 1/4 f of x minus g of x squared. So our final area is pi over 8 f of x minus g of x squared. So if we add up all of those areas, our volume equation would read the definite integral from a to b of pi over 8 f of x minus g of x squared. So we can simplify to pi over 8 times definite integral from a to b of f of x minus g of x dx. So down at the bottom, we ask the question, what do you notice about the integral sign formulas for finding the volume of solids with certain cross sections? So what I want you to do is basically just write down what do you notice about these final volume equations after we found the area of these cross sections. Okay. So very last page of notes. Region R is bounded by y equals sine pi x and y equals x cubed minus 4. We want to find the volume of the solid form in cross sections whose cross sectional shapes indicated below. Cross sections indicated to the x-axis. Great. So there are a few things that we need to know. First thing that we need to know is which function would be the upper function, which function would be the lower function in this situation. So we have two functions. We have this oscillating function and we have this curved function. The oscillating function very clearly is going to be our sine pi x function. Our curved function will then be x cubed minus 4x. Okay, now that we figured out which function is which, we're going to identify which one is the upper function and which one is the lower function. Looking at the shaded area that is drawn here, the upper function is the sine pi x function. Those are our upper function. And our lower function is x cubed minus 4x. The other piece of information that we're going to need to know, because if we're going to be finding volume of these solids using cross sections, we need to know our limits of integration. So our limits of integration are going to come from the start and end of the shaded area, which in this case is where these 2 points intersect. So 0, 0, and 2, 0. Okay. And since the problem tells us that all these sectors are perpendicular to the x-axis, it tells us that we're going to be using the x values for our limits of integration. So all these limits of integration will all be from 0 to 2. So then now we just have to figure out which cross sections we want. So for part A, we want cross sections that are equilateral triangles. So if I draw an equilateral triangle sticking out of this, so imagine those are equilateral triangles. Right, that means that we put the volume of, and we've already found the general equation for this on the previous page. So square root of 3 over 4 as the definite interval. We're going of our function I x minus our lower function x cubed minus 4x dx squared dx. And when we plug that into a calculator, we get 0.861 as the volume of that solid created by those cross sections. Now we want cross sections that are semicircles. Now I'm going to sketch a semicircle cross section or two. Right? And we've already identified the general form for those equations as well as pi over 8 definite interval from 0 to 2 of the outer function sine pi x minus the inner function 3x cubed minus plus 4x squared dx. When we plug that into the calculator, it's 3.918. So for C, we're looking at cross sections that are isosceles right triangles. I'm actually going to erase one of my semicircles so that I can draw this isosceles right triangle. Okay, so we have a general formula for that. That's E equals 1/2 definite interval from 0 to 2 of sine pi minus x cubed minus 4x squared dx. And plug that into a calculator, we get 0.989. And then part B, we're looking at cross sections that are squares. So if my cross section is a square, we've already found the equation for that. 0 to 2 of sine pi x minus x cubed minus 4x squared dx. That is equal to 9.978. Okay. So for E and F, we're looking at cross sections that are rectangles. We do not have a general equation for those, so we're actually going to create one as we go and use it to plug things in. So if we let sine x be our f of x function and x cubed to be our cube function, then when we draw this triangle, we can try to figure out what this is going to look like. So if I want a rectangle drawn here where the height is twice the length of the base, so it's going to be a very long rectangle. So here's the base. Our base is going to be our f of x minus g of x. That's the part that's on my actual shaded region. And then my height, part sticking out, is going to be 2 times my base, which is minus g of x. So if we look at this as the rectangle popping out of this section of paper, this is my f of x minus g of x, and this is my 3 times of x minus. And we know that the area of a rectangle is equal to b times height, so that would be equal to f of x minus g of x times 2 times f of x minus g of x, which is just equal to 2 times f of x minus g of x squared. So if I want to find the volume of the solid, I'm going to add up all of the rectangles, and we'll use definite interval from 0 to 2 of 2 times minus g of x squared dx, which is equal to 17.957. Okay, so for part F, we want cross sections that are again rectangles whose height is 1/3 the length of the base. So now I want a cross section that's a rectangle, and the height is going to be 1/3 less than the base. So this is going to be a smaller rectangle. So if I draw this as my base, it's not completely drawn to scale, of course. Do this. So my height is going to be a smaller piece. So if this is my base is still f of x minus g of x, because that's the part that's on my shaded area. And then my height is 1/3 of that base, f minus g of x. So again, my area is going to be those two things multiplied together, which will be 1/3 times f of x minus g of x squared. So volume will be definite integral from 0 to 2 of 1/3 of f of x minus g of x squared dx is equal to 3.326. Okay, so this is the final topic of the year, final new topic of the year. This topic is the culminating topic that actually includes the last few videos. It talks about the space in the shaded area and talks about the volume of that shaded area. So moving forward, all of our FRQs and practice is going to be a combination of not just this unit, but all the units as we review for both the AP test and the final exam, and as you work through the upcoming projects for this class.